Okay, this is problem 2.6 of Griffiths Quantum Mechanics Continued. Hopefully this section will go a bit quicker than the first section. Probably should have split it a bit differently. But this is the way the problem was split over the book, or at least the version of the book I have. Okay. This is a delightfully obscure reference, by the way. So we want to compute the expectation value of the momentum, and his hint is do it the quick way. That's from Arsenic and Old Lace, which if you're an undergrad, you probably have not heard of that. You should go watch it. It's worth your time. So we are going to do it the easy way. I did do it the hard way once, but I don't feel like writing that out. So I am just going to do it the easy way. So that's the expectation value is the mass times the time derivative of the expectation value of the position. Now, I wrote this down so that I won't forget. This was our expectation value for x. It was 16a over 9 pi squared. That's our amplitude. Our frequency is 3 times omega. So now I would like to get the expectation value of the momentum. So I am just going to take the time derivative of this, which is really, really easy. So that's just going to be mass. Oh, that's a 2. And then we have the derivative of the inside is 3 omega times the derivative of the outside, negative sine 3 omega t. So our omega, let's remind ourselves again, is pi squared h bar over 2 ma squared. So I have mass times 16a over 9 pi squared times 3 times pi squared h bar 2 ma squared sine omega t. Alright, my masses cancel, my pi squares canceled, and one of my a's cancel. And if you haven't guessed it already, yeah, we're gonna be checking the units on this. Okay, so then we have 16 divided by 2 is 8. H bar, 3 divided by, or 9 divided by 3 is 3. And then we have an A, and then we have sine omega t. Now, units. This is momentum. Still has units of kilograms times meters over seconds. What do we have? We have kilograms, meters squared over seconds. So h bar is joules times seconds divided by A, which is in meters. And it checks out. Since h bar is a constant, you might want to get used to the idea of momentum being expressed in inverse meters. It's just a lot more useful. And there we go. That was super easy. That was nice. Okay, let's go on to the next part. So this one should be relatively... Probably should have split it into problems A and B and then done C through F. Alright. Now we want to find the expectation value of H, the Hamiltonian. And we want to know how does that compare with E1 and E2. So, I want to find this and compare with energy 1 and energy 2. Now, to remind ourselves, the Hamiltonian operator is negative h bar squared over 2m second derivative of our expectation value with respect to x. Yep. Okay. Now, inside our infinite square well, our potential is 0. So our energy is... Oh, whoops, why did I write squared there? Is all kinetic. So let's go ahead and get our expectation value. That was negative 8h bar over 3a sine 3 omega t. So my expectation of my Hamiltonian is going to be 1 over 2m, and that expectation value squared. So we get a positive, we get 64 h bar squared over 9 a squared sine squared 3 omega t. I suppose I could simplify that a little bit. So again, we did it the very easy way. So that's 32 h bar squared over 9 ma squared sine omega t. Okay, now we always want to check our units, right? Hamiltonian has units of energy, and our Hamiltonian is kinetic plus potential. So we have joules plus joules. Here I have joules squared seconds squared over kilograms meters squared. So I'm going to leave a joule. I get another joule. I'm going to write this one as a kilogram meter squared over second squared times second squared over kilogram meter squared. My second squared cancels, my meters squared, kilograms canceled. I am left with joules, so we are happy. Now let's look at our energies 1 and energy 2. So that'd be n equals 1 pi squared h bar squared 2ma squared. Energy 2, our n equals 2, so we have 2 squared is 4. 2ma squared. See, this is probably a better way to take it, because Because let's look at this. Not dependent on time. Or at least I'm going to say on oscillation. Because there's an even easier way to look at it, which is probably why Griffiths told you to do it this way. Which is, let's look at this. There we go. Another thing that I want to make a note of here is that E2 is just 2 times bigger than E1. So E2 equals 2 times E1. Okay. And then there actually is a nice result in Griffiths. Let's see. Do I have it up? Okay, I found it here. So I can look at this and this, leading to this idea that the expectation value of the total energy is equal to just the energy level. Nice shortcut there. So basically, my expectation of the Hamiltonian is just the energy average. So I have 2 energy states. Oh, I made a mistake here. That's 4 times, not 2 times. Because that has a 2 and that has a 2. I don't know why I thought that was 2 times. Okay. So my expectation of my Hamiltonian is just my average energy. So that was 2.1. Equation 2.12. So from section 2.1, equation 2.12, we have this. So that means that my Hamiltonian is just going to be this guy, E1 plus E2, which is 4 times E1, not 2 times. So that's just going to be 5/2 E1, so I can write it like this. 2ma squared, or I could write 5/4. That was even easier. And there we go. That is our Hamiltonian. Now, let's look at the very last part. Alright, this one is another case where I'm not entirely sure I know what he was getting at. Which, you know, happens when you read textbooks, even when you've read a textbook a lot. Okay. So a classical particle in the swell would bounce back and forth between the walls. That's kind of what we think about happening, but the quantum situation is not exactly analogous to that. if its energy were equal to the expectation value we found in E, so if we had, let me look at a note here. So if I had my energy, like my average energy, was 5/2 of E1, or this 5/4 pi squared h bar squared over ma squared. Then it wants to know what is the frequency of classical motion and how does it compare with the quantum frequency I found in C. So in part C, we found that was 3 omega, or three pi squared. I'm just using F as a shorthand for frequency, not making the distinction between frequency and angular frequency here. Okay, so not entirely sure what he means. Like, I guess if it were bouncing back and forth, what would we expect the frequency to be? So I would just take like a simple idea of frequency being just frequency times h bar equals energy. Then I have frequency times h bar equals 5/4 pi squared h bar squared over ma squared. So what I get here is the frequency is this, or I'm just going to call that frequency prime to distinguish it, or I get a slight difference from what I had before. Incidentally, no, it still wouldn't have worked. I was just curious if E2 had really been 2 times bigger than E1, but no, because we had that extra factor of 2. So we'd have, like, I guess, classical. And this would be our quantum. I did this like all the ways that I could think of. Okay. Well, I guess if it were 2 times, let's see, it would have been exactly 1/2 the frequency. So we could call that, we could say this one we have 5/4 pi squared m over a, and then our quantum one would be 6 over 4. I was looking for a nice way to relate them. There really isn't. Except if I had been correct that the second energy level was just twice as much as the first energy level, then it would have been exactly half. But no, it's not really that nice. Okay. That was one way I interpreted that. I am not certain of that at all. So then I went back to just classical motion frequency, thinking about like a mass on a spring. That would be my interpretation of the word frequency, would be something oscillating on a spring, being the frequency being the square root of the spring constant divided by the mass, where the spring constant is the force divided by the displacement, and the force is the spatial derivative of the energy. So then I would find the force to be 5. So we have our energy, so I'm just gonna take the derivative of that, where I'm going to replace a with x squared. So then I get -2. So that'll just be 5 over 2. Pi squared h bar squared mx cubed. Never hurts to check the units. So I have kilograms meters squared. Kilograms, I have h bar squared. Kilograms squared meters to the 4th over seconds squared over kilograms over meters to the 3rd. Cancels 1 kilograms, cancels 3 meters, so I'm left with kilograms meters over seconds squared, which is force. Good. Math still works. It's encouraging to know. Alright, so that means that K is the force divided by I'll keep the negative so then they'll cancel out. So that's our force divided by displacement. So I just get x to the 4th down there. So my omega is the square root of K, and then that's going to be divided by mass. So now I'm just going to use the absolute value. 5/2. And then I take that divided by mass, so the mass is going to cancel out. So I just, oh no, it's not. It's just going to be squared. There we go. I suppose I should have written that a bit better. So 5 pi squared 2m squared x to the 4th. And that's what I get for my classical frequency, is square root 5/4 pi h bar over mx squared, or in particular with A squared That's another interpretation. Another way, which does end up giving us the same thing, just looking at even going further back. Force equals mass times acceleration. For something oscillating, acceleration is just the radius of acceleration, a times omega squared. I already found the force before, so I'm just going to use that same result. So I have 5 squared. You know, where did that 4 come from here? Let's go ahead and fix that. I don't know why I suddenly started writing the 2's as 4's. So that's 5 halves. There we go. Pi squared h bar squared ma cubed equals ma omega squared. So the a's cancel, the m goes the other side, so I get 5 halves. I get the exact same thing. So that one goes here. One of the a's cancels out. That equals omega squared. So then, which it should, I mean, they're came from the same place. Not sure if that's what he wanted or not, but that's my interpretation of it. I don't do a whole lot of classical mechanics, so my first impression would be this. That would be what I would always consider the frequency to be, because I would always consider solids. I suppose this makes more sense if you're more keen on rotation. At any rate, there's something there.